The Large Hadron Collider, a gateway to cosmic secrets or a Pandora's box. Deep beneath the Franco-Swiss border lies a marvel of modern science, a 17-mile ring of superconducting magnets known as the Large Hadron Collider, LHC. Operated by the European Organization for Nuclear Research, CERN, the LHC is the world's largest and most powerful particle accelerator. This colossal machine is designed to probe the fundamental building blocks of the universe, recreating conditions that existed mere fractions of a second after the Big Bang. It stands as a testament to human ingenuity, ambition, and our relentless quest to understand the cosmos. Yet, as we stand on the precipice of unlocking nature's deepest secrets, questions linger. Could this machine, built to illuminate the universe's origins, inadvertently unleash forces beyond our control? Recent statements from prominent physicists, including Brian Cox, have reignited fascination and fear about the LHC's potential. This article explores the LHC's purpose, its awe-inspiring capabilities, and the profound risks that accompany humanity's boldest scientific endeavor. What is the Large Hadron Collider? The LHC is not merely a machine. It is a triumph of engineering and a symbol of international collaboration. Located 100 meters underground, this circular accelerator spans 27 kilometers, crossing the border between France and Switzerland. Its purpose is to accelerate subatomic particles, primarily protons, to nearly the speed of light before smashing them together in high-energy collisions. These collisions generate conditions so extreme, temperatures millions of times hotter than the sun's core, that they mimic the universe's state moments after its birth 13.8 billion years ago. The LHC relies on a complex network of thousands of superconducting magnets, cooled to minus 271 degrees Celsius, colder than outer space, using liquid helium. These magnets guide proton beams along precise paths, ensuring they collide at 4 designated points around the ring. At these collision sites, massive detectors, ATLAS, CMS, ALICE, and LHCb, act as high-tech cameras, capturing data from the particle collisions. Each detector has a unique role. ATLAS and CMS search for new particles like the Higgs boson. ALICE studies a quark-gluon plasma that existed in the early universe, and LHCb investigates the asymmetry between matter and antimatter. Together, they produce petabytes of data, which scientists analyze to uncover clues about the universe's fundamental forces and particles. The LHC's crowning achievement came in 2012 when ATLAS and CMS confirmed the existence of the Higgs boson, a particle theorized to give other particles mass. Dubbed the God particle by the media, the Higgs was a missing piece of the standard model of particle physics, the framework that describes how particles and forces interact. This discovery earned CERN global acclaim, but also raised new questions. What else lies beyond the standard model? Could the LHC reveal the nature of dark matter, the mysterious substance that constitutes 27% of the universe's mass? Or could it probe extra dimensions, challenging our understanding of reality itself? CERN, a hub of scientific excellence. Founded in 1954, CERN is one of the world's most prestigious scientific organizations, with 23 member states and contributions from thousands of researchers worldwide. Based in Geneva, Switzerland, CERN fosters collaboration among physicists, engineers, and computer scientists, driving innovation in particle physics and beyond. Its accelerators, including the LHC, form a sprawling network designed to explore the subatomic realm. While the LHC is CERN's flagship project, the organization also operates smaller accelerators and experiments, each contributing to our understanding of the cosmos. CERN's work extends beyond particle physics. Its technologies have led to advancements in medical imaging, cancer treatment, and even the creation of the World Wide Web, developed at CERN in 1989 to facilitate data sharing among scientists. Yet, the LHC remains the heart of CERN's mission, embodying humanity's desire to unravel the universe's mysteries. By studying the infinitesimally small, particles a billionth of a meter in size, scientists gain insights into the vastness of the cosmos, from the birth of stars to the expansion of space itself. How the LHC works: a cosmic racetrack. Imagine a racetrack where the competitors are not cars or athletes but protons, tiny particles found in the nucleus of every atom. The LHC accelerates these protons to 99.9999991% the speed of light, a velocity so fast that they circle the 27-kilometer ring 11,245 times per second. To achieve this, the LHC uses electric fields to boost the proton's speed and magnetic fields to steer them along their circular path. The protons travel in two beams, each containing billions of particles, which are made collide at the four detector sites. These collisions are not random. They are carefully orchestrated to maximize scientific output. When protons smash together, their energy transforms into a shower of new particles, some of which exist for only a fraction of a second before decaying. The detectors capture these fleeting moments, recording the particles' properties, mass, charge, and trajectory. By analyzing this data, scientists can identify known particles, search for new ones, and test theories about the universe's fundamental laws. The conditions inside the LHC are extraordinary. The collisions produce temperatures exceeding 10 trillion degrees Celsius, far hotter than any naturally occurring phenomenon. Meanwhile, the superconducting magnets operate at temperatures close to absolute zero, creating a stark contrast between the fiery collisions and the frigid infrastructure. This delicate balance of extremes showcases the LHC's engineering prowess and the precision required to probe the subatomic world. The quest for the unknown. The LHC's primary goal is to deepen our understanding of the universe's fundamental building blocks. The discovery of the Higgs boson was a milestone, but also opened the door to new mysteries. For example, the Standard Model cannot explain dark matter, dark energy, which drives the universe's accelerated expansion, or why matter dominates over antimatter. The LHC's experiments aim to address these gaps by searching for new particles or phenomena that could extend or replace the Standard Model. One tantalizing possibility is the detection of supersymmetric particles, hypothetical partners to known particles that could account for dark matter. Another is the exploration of extra dimensions, predicted by theories like string theory. These dimensions, if they exist, are compactified at scales too small to detect under normal conditions. The LHC's high-energy collisions could, in theory, provide enough energy to access these hidden realms, offering a glimpse into the structure of reality itself. Yet, with every discovery comes a new challenge. The more we learn, the more we realize how much remains unknown. The LHC is not just a tool for answering questions. It is a catalyst for asking new ones, pushing the boundaries of human knowledge and imagination. The risks of probing the unknown. The LHC's power is both its greatest asset and its most concerning feature. Recreating the conditions of the Big Bang, even on a microscopic scale, raises profound ethical and existential questions. What are the risks of manipulating the fabric of space and time? Could our pursuit of knowledge inadvertently trigger catastrophic consequences? These concerns. Another concern involves the Higgs boson itself. In his writings, the late Stephen Hawking warned that the Higgs could become unstable at extremely high energies, potentially triggering a phenomenon known as vacuum decay. This catastrophic event would involve a bubble of true vacuum expanding at the speed of light, obliterating everything in its path, planets, stars, and the universe itself. While Hawking acknowledged that such an event is unlikely within the LHC's energy range, his cautionary words underscore the need for vigilance. Sir Martin Rees, a renowned British cosmologist, has also expressed concerns about particle accelerator experiments. In his book on the future, Prospect for Humanity, Rees explores the risks of probing the unknown, including the possibility of vacuum instability. He argues that even a minuscule chance of a cosmic catastrophe warrants serious consideration, given the irreversible consequences. Rees's warnings are not rooted in fear-mongering, but in a sober assessment of the uncertainties inherent in cutting-edge science. A cautionary tale, the Anatoly Bugorsky incident. The dangers of particle accelerators are not purely theoretical. In 1978, Russian physicist Anatoly Bugorsky experienced a harrowing accident that highlights the raw power of these machines. While working on U-70 synchrotron in Propvino, Russia, Bugorsky accidentally placed his head in the path of a proton beam. The beam, traveling at nearly the speed of light, pierced his skull, entering to the back of his head and exiting through his nose. Bugorsky described seeing a flash brighter than 1,000 suns, yet he felt no pain. The beam's path caused severe damage, burning through tissue and bone. Remarkably, Bugorsky remained conscious and walked to a clinic for treatment. The aftermath was both tragic and astonishing. He lost hearing in one ear, suffered partial facial paralysis, and experienced seizures, yet his cognitive abilities remained intact. Bugorsky continued his scientific career, becoming a living testament to the destructive potential of particle beams and the resilience of the human spirit. This incident serves as a stark reminder of the forces at play in particle accelerators. While the LHC operates under stringent safety protocols, the Bugorsky accident underscores the need for caution when dealing with energies that dwarf human comprehension. Brian Cox's revelation, a mini Big Bang. In recent years, physicist Brian Cox, a former CERN researcher and prominent science communicator, has brought renewed attention to the LHC's ambitions. Cox has described the LHC's goal in stark terms: to recreate a mini Big Bang, a controlled replication of the universe's birth. By smashing protons together at unprecedented energies, the LHC generates conditions akin to those that existed 13.8 billion years ago, offering a window into the cosmos' infancy. Cox's announcement is both exhilarating and unsettling. The ability to simulate the Big Bang holds immense promise for understanding the Higgs boson, dark matter, and the forces that shape our reality. Yet, it also raises a haunting question. What if something goes wrong? The LHC's collisions involve energies far beyond those encountered in everyday life, and the consequences of an error, however unlikely, could be profound. Cox has emphasized that the LHC operates within safe parameters. The energies involved, while immense by human standards, are comparable to those produced by cosmic rays, high-energy particles from space that strike Earth daily. Moreover, rigorous safety reviews and simulations have concluded that the risk of creating a stable black hole or triggering vacuum decay is negligible. Any black hole produced would be so tiny and short-lived that it would pose no threat, evaporating in a burst of Hawking radiation. The allure of the unknown, portals and parallel dimensions, beyond black holes and vacuum decay. Some have speculated that the LHC could open a portal to another universe or dimension. While this idea is largely dismissed by mainstream scientists, it has captured the public's imagination, fueled by science fiction and sensationalist media. The concept originates from string theory, which posits the existence of extra dimensions beyond the familiar three of space and one of time. These dimensions, if real, are compactified at scales too small to detect under normal conditions. The LHC's high-energy collisions could, in theory, probe these hidden dimensions, revealing new particles or phenomena. Some have even suggested that the LHC could act as a cosmic key, unlocking pathways to parallel realities. While such claims are speculative, they highlight the profound implications of the LHC's work. By pushing the boundaries of physics, CERN is venturing into uncharted territory, where the line between science and science fiction blurs. Balancing discovery and responsibility, the LHC is a monument to human curiosity, a tool for exploring the deepest mysteries of existence. Its discoveries have reshaped our understanding of the universe, from the Higgs boson to the potential for new physics. Yet, it also serves as a reminder of the responsibilities that accompany great power. The risks, though small, are not zero, and the consequences of a misstep could be catastrophic. CERN scientists are acutely aware of these concerns. The LHC's operations are governed by rigorous safety protocols, peer-reviewed studies, and international oversight. Calculations show that the probabilities of creating a stable black hole or triggering vacuum decay are astronomically low, far less likely than natural cosmic events that have occurred for billions of years without incident. Moreover, the LHC's energies are well within a range of those produced in nature, providing a reassuring benchmark. Still, the ethical questions persist. How far should we push the boundaries of knowledge? Are we prepared for the consequences of unlocking forces we do not fully understand? These questions are not unique to the LHC. They echo throughout history, from the development of nuclear energy to the advent of artificial intelligence. The pursuit of discovery has always carried risks, but has also driven humanity's greatest achievements. A dance with the cosmos. The Large Hadron Collider stands at the intersection of science, philosophy, and ethics. It is a beacon of human achievement, illuminating the universe's origins and challenging our understanding of reality. Yet, it is also a reminder of our fragility, a testament to the delicate balance between curiosity and caution. As we peer into the subatomic abyss, we must confront the possibility that some secrets are best left undiscovered, or at least approached with the utmost care. Brian Cox's words resonate as both a promise and a warning. The LHC holds the power to recreate the Big Bang, to conjure the essence of creation itself. But with that power comes a responsibility to wield it wisely. The LHC is not just a machine. It is a mirror reflecting our ambitions, our fears, and our place in the cosmos. As we continue to probe the unknown, we must do so with humility, recognizing that the universe is vast, mysterious, and not always forgiving. The question remains, are we ready for what lies beyond the next collision?